Have you ever thought about what the word infinity actually means? You could say unlimited, endless, or without bounds, but what does that actually mean? George Cantor drove himself to insanity in his unwrapping of infinity. First, Mr. Cantor looked at infinite sets starting with the counting numbers. In his search determination, he realized if he added 1 to a counting number, a new counting number would form, never allowing him to reach an end, hence their infinite supply. The set of counting numbers in any other infinite set that could be compared using one-to-one correspondence was countably infinite. For instance, if you have an infinite list of even counting numbers and a list of all counting numbers, you would assume that the list of all counting numbers would be larger, although every counting number has a corresponding even number. This pattern will go on for infinity, and both of these lists hold the same amount of numbers. Mr. Cantor still wasn't convinced on what the definition of infinity was, so he explored further into cardinality. For example, a finite set of 1 through 5 has a cardinality of 5 because it contains 5 values. When it comes to infinite sets, the cardinality is much more complex, but Mr. Cantor remembered that if two infinite sets can be compared using one-to-one correspondence, they contain the same cardinality, but he didn't know what to call this infinite cardinality, so he came up with the symbol aleph null. But what about the cardinality of infinite sets that aren't created equal? To answer this, Mr. Cantor explored subsets. For example, if we have the set 1, 2, 3, we can form 8 total subsets using the formula 2 to the power of n being the cardinality. So how many subsets can we make from a countably infinite set? Well, if the cardinality of a countably infinite set is aleph null, the number of subsets must be 2 to the power of aleph null. George realized this new number was more than countably infinite, which led him to his diagonal proof. George assumed counting in real numbers could be paired off using one-to-one correspondence, hence have equivalent cardinalities. He started examining the correspondence between real and counting numbers and soon realized you could list any real number next to a counting number and not be able to keep track of the numbers because there is no pattern in the correspondence. So Mr. Cantor focused only on real numbers between 0 and 1 to form this hypothetical list using dn. However, Mr. Cantor came up with a real number that doesn't fit anywhere in this infinite set. He called this number m and found it using the diagonal components of his hypothetical list and added 1 to each of them. The real number m will be an extra number in his one-to-one correspondence, so we can assume our original assumption was wrong. You might ask, can't we add 1 to every real number and add m? The answer is no. Knowing if we have a new list with every number plus 1, we can simply add another 1 to the diagonal components to find m2, which again doesn't have a place in the set. We continually make new extra real numbers, m, m2, m3, etc., giving us an infinite amount of extra real numbers, so the infinite set of real numbers isn't a countable infinity. Mr. Cantor named this new infinity uncountable. An uncountable infinity is larger, giving it a contrasting cardinality. Mr. Cantor assumed the cardinality would be 2 to the power of aleph null, or aleph 1, because it is only slightly larger than aleph null. Overall, Mr. Cantor used his diagonal proof to show some infinities hold different cardinalities. Therefore, there is no precise definition of infinity, as there are multiple types of infinity, countable and uncountable. Thanks for watching!